Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets review for October of 2022. And I want to start out this month with a new category that I'm calling the State of the Field, which is where I'll be putting any papers or stories that are more about the field of exoplanets as a whole rather than specific discoveries. And I created this category for this report, Community Report from the Biosignatures Standards of Evidence Workshop. I've had the opportunity to cover a few papers like this before, but I didn't feel like they fit in the original format of these videos. They're white papers, not research, not journal articles, or anything like that. So they aren't exactly about the new science, but they're still important because they're about how we do the science. And this one felt important enough to the field going forward that I thought I needed to cover it, and I realized a separate category would be a good fit. And essentially this is the exoplanets community with all of these authors getting together and saying, we need to be clearer about how we talk about biosignatures, and that's any sorts of signs of life on other planets, usually exoplanets. Because, long story short, any talk of aliens gets overhyped in the media, and the science gets distorted, sometimes even to the point of misinformation. And, quite often, speculative or tentative science gets reported as, if not certainty, then very likely. And the classic example of this was the Martian meteorite from 1996, where they put it under an electron microscope and found things that looked like fossilized bacteria. Now, they weren't. For one, they were actually too small. The scale on that image is not what it looks like. And for another, there are other non-biological sources for rock crystals that look like that. And this is a problem that continues when we talk about biosignatures today. From the interstellar asteroid Oumuamua to the phosphine on Venus to the detection of water on K218b. All of these things sound like they could be signs of life, but they're really not. And the reason is that there are a lot more uncertainties than what gets reported in the media. Sometimes the results are not as clear-cut as people like to say. Sometimes there are other interpretations, other ways the results could occur that don't involve life. There are any number of things we don't know about. And as I said before, the media often reports certainty where there is none. And it is increasingly likely that we will find biosignatures, or at least we'll be able to find biosignatures in the foreseeable future. If we get extremely lucky, maybe JWST will turn up something. Certainly we have concrete plans to launch a telescope that could find them by 2050. And so the community got together with 125 leading scientists to discuss a framework for biosignature detection that could handle these problems and communicate better just how certain they are. This is not a precise scale. There are several areas where astronomers favor scales. There's the Torino scale for asteroid impact hazards, for example. This group did not create a scale and may not do so in the future, but did discuss an understanding of standards that need to be met to verify biosignatures. And they basically addressed the concerns I mentioned earlier with this 5-step process. First, is it a real signal or is it just noise? Second, have other sources of the signal been ruled out, including sources on Earth? There have been times when radio signals bouncing off the atmosphere have been mistaken for signals from space, for example. Are there possible abiotic sources for the signal? And one famous theoretical example, we think that on M-dwarf planets, they could actually build up atmospheres with large amounts of free oxygen just from exposure to ultraviolet light from their stars, not from any life-based processes. Fourth, is it likely that life would produce this signal in this environment? And the phosphine on Venus is a good example of that, where it's not obvious where it came from. Phosphine can come from life on Earth, but it's not very plausible, based on what we know about life, that it would occur in the upper atmosphere of Venus. Even if the temperature is all right, there are a lot of other environmental problems with that. So this is sort of like Carl Sagan's extraordinary claims require extraordinary evidence. And I think actually recognizing that there are different degrees of extraordinary. Finding aliens in general would be an extraordinary claim, but finding them in a place where we don't expect anything to be living is that much more extraordinary. And fifth is, can we back it up with other observations? If we see phosphine and think it might be a biosignature, can we also find methane or free oxygen or nitrogen oxides or other molecules that would be additional biosignatures? And if we can back up one signature with evidence from others, that's a much better sign that we've found life. So that's the main development on the state of the field, and I think it's a very important development to keep working on as we go forward with observations that are starting to get into the territory where we could find life. Now, for the regular scientific reporting, there were a couple of interesting planets. I've got a pair of papers that are kind of similar to each other, talking about two specific planets, TOI 561b and TOI 1075b. And these are both ultra-short period planets, which would probably look similar to this. These are planets with an orbital period of less than 24 hours, not rotation period, although they will be tidally locked, but actual orbital period. And they are both in this interesting middle ground between Earth-sized and Neptune-sized. And more importantly, at least one of them is probably not rocky. Now, with planets orbiting this close to their stars, we don't really expect them to have an atmosphere. Almost any plausible formation model, the atmosphere gets blown off into space if they're that close. But we have one example of a planet where that's clearly not the case, and that is 55 Cancri e, which is larger in radius, and I believe lower in density than both of these new discoveries. It is too large to be rocky, and it is very hot. Temperatures of 1500 Kelvin, or even a little lower, we would expect the surface to be partially molten. At the temperature of 55 Cancri e, 2100 Kelvin, we would expect the surface to be entirely molten. This is completely a lava world, and we're not really sure what the atmosphere is made of, but its radius is large enough that it has to have a quite significant one. And you can see the planets plotted on this chart, in the typical mass radius diagram. We're interested in planet B for TOI 561, and I've drawn in 55 Cancri e and TOI 1075b. And you can see they're all close to the rocky planet composition lines, and it's easier to see if you look at radius versus density. So TOI 1075b falls right along the blue line, which suggests an Earth-like composition. It probably is completely rocky. 55 Cancri e and now the new planet TOI 561b both fall close to the green line, and the green is a pure rock composition. The thing is, we don't expect any planets to be pure rock. They're going to have some iron, and that means they need to have some water or some hydrogen or maybe some oxygen, like I said before, to create an atmosphere with a significant depth to make up that difference in radius. And keep in mind, the mass and radius measurements are estimates, and if you look at the margin of error for TOI 561b, it's actually possible that it is fully rocky and we just have the measurements a little bit off. This plot shows regions of likelihood, and it's kind of overlapping with the Earth-like composition. So we need more precise measurements, maybe with the Cheops satellite, to be sure of what we're seeing here. Another interesting planet that is of an unusual size is TOI 3884b, and this is a planet of 6 Earth radii. And that's unusual because if you look at the chart, there are a lot of planets with radii smaller than Neptune, and a lot of planets the size of Jupiter or Saturn or larger, and not many in between. That's suspected to be a quirk of formation that we don't fully understand yet. And it doesn't look especially remarkable on this radius versus stellar flux diagram. But this planet is very interesting because it is a prime target for spectroscopy. The transmission spectroscopy metric is a measure of how easy it should be to spot molecular features in its transit spectrum, and it is very high, near the top, and in fact it is much higher than any other known planets of a similar radius. So anytime you have a target that is very easy to observe and way off by itself in the parameter space of plots like these, that is some very important science that needs to be done. So I expect to see observations of that in JWST Cycle 2. And finally, we have some news from the HR 8799 system. And this system is famous for being by far the best observed directly imaged planet system, where telescopes like the Keck telescopes in Hawaii have spotted 4 visible planets in the infrared and have been tracking their orbital motion for years. And these planets are very widely separated. I can plot Neptune's orbit on this image, and you can see 2 of them are well outside Neptune's orbit. So this is a very wide system. And what this team did was look at all the images and look very close and see if they could tease out any additional planets from the mess of data near the star. The middle of the image is a mess because they're trying to block out the starlight, and that's not an exact science because of turbulence in the atmosphere and defects in the mirrors. So they're only getting it approximately, so you need to look very carefully to see if there's anything else there, and they actually did find a potential planet F that is inside the orbit of planet E. So this may be a 5 directly imaged planet system, so that is exciting. As usual, from individual planet discoveries to populations, this was an interesting paper, a catalog of habitable-zone exoplanets. This isn't really a new discovery, it's compiling previous discoveries, and there's not a lot to show for this one per se, but it's sure to be a very valuable reference paper, because it lists all the planets we know of that are in the habitable zones of their stars. And this includes both Earth-sized planets up to gas giants. And you can see them on this plot as the green squares. And they occur at a range of orbital periods because they orbit different sized stars. So that is sure to be a valuable reference as we go forward, looking for biosignatures. For some more direct measurements, we have the occurrence rate of hot Jupiters around early type M dwarfs based on test data. And this is based on the fact that hot Jupiters are the first type of exoplanet to be discovered, but they are uncommon. Only about 1% of stars have them, and that is for sun-like stars. For M dwarfs, because they don't form giant planets as easily, we expect them to be considerably rarer. And this paper looked through the data from the TESS satellite, tracked down the few hot Jupiters that TESS has spotted around red dwarfs, and extrapolated that to how common they are around all red dwarfs, and indeed, they are quite rare. Only about 0.25% of red dwarfs appear to have hot Jupiters. So that's an important data point for planet populations. There were a few interesting papers about planetary atmospheres in October, but I want to start with one that is actually about planetary surfaces. And this is a laboratory study to support spectroscopy of lava worlds. And as I mentioned, this is one of the puzzles of exoplanets that we're still trying to solve. And we need to be able to take spectra of these lava worlds to solve them. The thing is, we don't have very many spectra, especially reflection spectra, for reflected starlight, of what we expect the surfaces of lava worlds to look like. And laboratory measurements are the gold standard. There are people who do purely theoretical calculations based on the quantum mechanics and calculating what all the electron transitions will be, and that's good, but it's no substitute for laboratory measurements. And there are not enough people doing those kinds of measurements, so this is a very important contribution to the field, where they did laboratory measurements of 16 different lava world surface compositions. And if you're a geologist, you will recognize where they fall on these charts. The important thing is they covered a fairly wide range of different lava types. And they got reflection spectra in the infrared that look like this. And this is prime JWST territory with those strong silicate features at 10 microns. So if it can get a reflection spectrum of a planet like 55 Cancri E or the others I mentioned earlier, this is where you'll want to go to analyze their composition. Meanwhile, in atmospheres, there was another paper on HR 8799, specifically Planet C, retrieving the carbon and oxygen abundance for this planet by combining high and low resolution spectrum data. And this is important because we believe that the carbon to oxygen ratio is a signature of how planets formed, and for HR 8799c, it seems to be pretty close to a solar C to O ratio, which suggests that the planet may have formed out of the primordial nebula rather than forming in the disk and migrating outward. And there's a nice temperature profile of the atmosphere as well. In October, we also had the first transmission spectrum of a sub-Earth-sized planet. I'm pretty sure it's the first spectrum of a sub-Earth-sized planet, L9859b, and this is the band used on Hubble. It has a nice water absorption feature right in the middle, so if there's any water vapor in the atmosphere, it should show up here. And predictably, like pretty much all of the spectra of small planets we've seen so far, it is flat. Or at least statistically close enough to call it flat. Now, JWST should change that because it can go much farther into the infrared, but right now it's flat, so they can't really say anything, probably just clouds. Now, you will note the yellow line in this figure, which is H2 dominated plus HCN. And I thought this was interesting because there was another paper analyzing these same Hubble data for L9859b by this Chinese team, and they found what seems to be a fairly strong fit with an atmosphere containing clouds and nitrogen rather than hydrogen plus HCN. That's hydrogen cyanide. And hydrogen cyanide is a gas that we expect to form in some quantity in primordial atmospheres. Some theories of the origin of life on Earth actually feature it quite heavily, but we don't expect to find it in isolation. That speaks to an improbably high nitrogen abundance that we don't see together with any oxygen-bearing compounds. So this is sort of like what I said at the beginning about plausibility. It's possible that this is a hydrogen cyanide spectral feature, but it's not especially plausible to see it in the absence of oxygen. So that may need some follow-up, but I am skeptical of that fit and am inclined to go with the pure cloud fit, which is a flat spectrum. We got some new climate models of exoplanets, and this is a three-dimensional cloud model of planets with high axial tilts. And it's a little complicated, but this is a temperature map in latitude versus time, month of the year, for otherwise Earth-like planets with different axial tilts. So in the top right, you have Earth, 23.5 degree tilt, where the band of warm temperatures fluctuates north and south over the course of the year. And that's where we get our seasons. In the top left, you have 0 axial tilt, where it stays completely flat. And then on the bottom, you have 45 degrees and 60 degrees, which interestingly come out significantly warmer. And in the 60 degree case, you wind up with polar hotspots. And similarly, we have precipitation rates and wind speeds. So if you're into exoclimate modeling or world building on alien planets, that may be a paper you want to check out more thoroughly. And one more atmosphere paper, Survival of Terrestrial N2O2 Atmospheres in Violent XUV Environments Through Efficient Atomic Line Radiative Cooling. And this was an interesting one, talking about mainly habitability around M-dwarfs, which of course is a hot topic of debate these days. The issue is that if you have a potentially habitable planet orbiting an M-dwarf, even if there's no hydrogen, a nitrogen-oxygen atmosphere like Earth's could still be evaporated by the intense ultraviolet light from the star. However, nitrogen and oxygen cool more efficiently than hydrogen. Line cooling is the emission of light through molecular transmissions rather than just a black body, and it is more efficient than blackbody radiation and is especially more efficient for what we call metals like nitrogen and oxygen rather than hydrogen and helium. So this team created models of mass loss with line cooling included, looked at the temperature of the upper atmosphere versus ultraviolet flux, and the erosion rate of the atmosphere in billions of years needed to strip it away, and they found that line cooling did significantly improve the survival of these atmospheres. So that's 1 point in the habitability column. And after all these atmosphere papers, we have some fun speculative papers. The first one is still climate related, but in a little bit of a different direction. CO2 ocean bistability on terrestrial exoplanets. So this is something that I haven't talked a lot about in the past, but is pretty important in exoclimatology and habitability, and that is climate bistability. And this is the result that some models of climate for quote-unquote Earth-like planets will jump between one climate state and another without much in between. And the classic example on Earth is the transition from the snowball Earth, where the oceans are completely frozen over, to a modern temperate climate or even hothouse climate where there are no ice caps. And some models can have 3 or 4 states, and on the high temperature end, a runaway greenhouse is usually one of them. But the important thing is that a planet can skip between multiple stable states. And this is a classic model from 2010, showing as you increase the amount of sunlight Earth receives, there are both snowball states and warm climate states that overlap with each other, but Earth is very likely to be in one or the other, not in between. Well, this new model includes CO2, and this is sort of a counterintuitive result, but if CO2 levels are high enough, and I mean tens of atmospheres, so thousands of times higher than we have on Earth, it can actually cause a cooling effect due to increased Rayleigh scattering. So the same effect that makes the sky blue, if you pile up enough air, will actually reflect some sunlight into space and cool off the planet. But again, that requires tens of atmospheres of CO2. So it's far outside our experience on Earth. And the interesting thing is, when you pile up this much CO2 and let it cool, then you can get liquid CO2. That's actually not possible at Earth's atmospheric pressure. You go directly to dry ice under those conditions. But in this new model, with enough gaseous CO2 on top, it can happen. But as the CO2 liquefies, the atmospheric pressure drops, the Rayleigh scattering decreases and falls below the turnover point where the CO2 starts warming again, and that boils off the ocean. So you have this potentially cyclical climate over millions of years between a CO2 ocean and a thick, all gaseous CO2 atmosphere. So not exactly a new climate state for Earth, but could apply to some exoplanets. And actually could maybe apply to certain periods of Venus's past, although I don't believe that was mentioned in the paper. There was a paper on exomoons and how they could affect the dynamics of planets through tidal forces. And this is based on what we know about our own moon, which is tidal forces can cause a moon to migrate towards or away from its planet. If the moon is above the geosynchronous orbit like our moon is, it migrates outward. But if it's below the geosynchronous orbit, like Mars's moon Phobos, it actually migrates inward. And the other important thing to remember is that there's not enough angular momentum in the Earth-Moon system to actually eject the moon from Earth orbit, but there could be for exomoons. And in any case, moons could collide with their planets under tidal forces. And the important thing about moons colliding with their planets is that it will produce large amounts of dust. And this dust will produce huge clouds that will block some of the starlight and potentially be visible from Earth. And for close-in planets, tidal forces from the stars are stronger, so they are more likely to collide with their planet or be ejected and then fly around and maybe collide with the planet later. And we know of quite a few young stars with dust disks, and that's expected from planet formation. But there are a handful of older stars with thick dust disks. And that's a little harder to explain. And one possible explanation, although probably not all that likely at this point, is collisions of exomoons with planets. So this is very speculative, and I'd be willing to bet against it that there are probably other explanations for these older stars that have dust disks, but it's something to keep in mind. And a couple of papers about aliens, of course. First, galactic settlement of low-mass stars as a resolution to the Fermi paradox. And the Fermi paradox is the classic paradox that if there are spacefaring aliens out there, statistically they have probably had plenty of time to colonize the universe, and could have colonized our solar system millions of years ago before we came along. So, if we think life is common in the universe, which most astronomers do, although not necessarily intelligent life, why hasn't that happened? And this hypothesis states that maybe aliens are not interested in sun-like stars. Low-mass stars are closer together, and we think that their planets remain habitable for longer, so they would probably be more appealing targets for colonization to aliens. And they suggest looking for technosignatures, that is, signs of technological life, around low-mass stars rather than sun-like stars to place better constraints on whether there are aliens lurking around the galaxy. I think that argument's a bit weak because low-mass stars are closer together, but if you add in sun-like stars, they're about the same distance from the next low-mass star over. So, I'm not sure if that argument really holds up, but it's an interesting resolution to the paradox. And finally, we have the exploration of M31, that's the Andromeda Galaxy, via black hole slingshots, and the intergalactic imperative. So this is a model how we could potentially send spacecraft to another galaxy. Conventional methods don't work because even if you get up to 0.1% the speed of light, you're not going to get a spacecraft to Andromeda before it collides with the Milky Way. But by slingshotting around a supermassive black hole, or better yet, a smaller black hole that's orbiting the supermassive black hole, you could get a spacecraft up to a large fraction of the speed of light without needing fancy nuclear engines or light sails or things like that that are still speculative. Now, getting a spacecraft to the center of the galaxy to make that slingshot maneuver is difficult, and they had a whole idea about using white dwarfs as an in-galaxy slingshot network. But the main thing is, even with foreseeable space travel technology, this suggests it would be possible to have robotic colonization between galaxies, which of course makes the Fermi paradox even harder to solve. And the intergalactic imperative is basically the dark forest or grabby aliens theory that has been circulating around the internet for the past few years, where you colonize all available planets to prevent competition from evolving and or moving in on your turf. Again, I think this one's pretty out there. It's a viable method of intergalactic travel, but I am very skeptical about reading anything into it about aliens because it's a multi-million year endeavor for a questionable payoff. So, doable, but I don't think really has any philosophical implications. So that's all for October. Be sure to tune in for next month's episode because there were some great new JWST results that I will be sure to cover.